So thank you everyone for coming. We're really excited to have everyone here to support our sponsored U of H seniors. So I'm going to go ahead and kick it over to Harshal and Kian. So they've been sponsoring and advising these seniors. So I'm going to kick it over to them for a more formal introduction. And just so everyone knows, please stay muted throughout the presentation. You will be able to be a short question and answer section at the end. And then also if you could go to speaker view, which will make sure whoever's speaking is the largest on the screen. That will help with the presentation as well. So I'll pass it over to Harshal.
Hi everyone, so this is Harshal Patil. I've been working in the cybersecurity group along with Kian as a cybersecurity engineer, and we had this project with University of Houston where 4 students who are in their senior year are doing their Capstone project, and the idea was to come up with like a model which can be like a prototype for what we see on actual vessels. So what was envisioned as part of this project was to create a propeller and rudder model that will be useful in future in order to do some kind of a cyber attack scenario. Right now, with help of the 4 students, Sean and Josh, who are electrical engineers, and Ryan and Daniela, who are mechanical engineers, a model has been created, and today there will be like a presentation about what the actual work was done, and also we will have a short demo of the actual model that is currently in the cyber lab in the ABS office. So I will let Josh introduce himself. He's in the lab here, and then Ryan will start with the presentation, and then we will switch back to the demo of the product. All right. Josh.
I'll introduce myself while Josh is trying to get on the camera. But I'm Ryan Miles. I'm one of the mechanical engineers, and I'll be graduating this fall, like my peers, with a major in mechanical engineering and a minor in mathematics.
My name is Daniela Quevedo. I will also be graduating this fall in mechanical engineering with a minor in math. And I'm really excited to just start working and get out in the real world. And then Sean.
Yeah, no, I'm a electrical engineer studying embedded systems. And yeah, we're graduating in a couple weeks.
Yep. And I'm Josh, Electrical Frenchwood. I'll be giving your demo for today after the presentation. Study electrical engineering as well with concentration on embedded systems. And I'll pass it over to Ryan so that he can present the slides for us.
All right, everybody's able to see the slideshow? Okay, great. So our capstone name is the Team 3 ABS Cougs. And like we just said before, we have Joshua Frenchwood, Daniela Quevedo, Sean Schupach, and myself. And our sponsor was you guys, the American Bureau of Shipping. And we developed a rudder propeller control system for cybersecurity penetration testing. So what we're going to give you guys in this presentation is just the motivation and the context and the background pertaining to why we needed to make this project for you guys, our statement of our year-long goal and the deliverable, how we validated what we were doing throughout this project, and our methodology into building the system. And then we'll explain to you guys and show you all the results and accomplishments and the kind of the road into getting to those results and accomplishments. We'll hit some of the challenges, and Josh will show you guys a demo at the end after we conclude this presentation here. So the motivation and context of this project was the American Bureau of Shipping wanted to presented to U of H students this project as a hardware or software system that acts. It's modeled after the systems that are on water in real time. And some of the I guess so that Harshal and Keon kind of gave us the option to either have hard-coded inputs or manual controls. And you'll see a little bit later on that we decided to go with manual controls for the network control system, which we chose. And that will be the rudder and propeller control systems.
So our project is made up of a control system, which includes our client goals, which under this, we have a system with multiple measurement capabilities. So we have a measurement at the bottom, a physical measurement, and then we also have little angle measurements on the track that you can see a little, as well as the screen will show you how fast and where the rudder is. And we also made it software driven. And then another part of our project is the IoT application, which includes the accuracy goals. And this includes that the rudder will be no greater than or less than 0.5 degrees off, and our propeller will be no greater than or less than 30 RPMs, and the software lag will be less than 200 ms. And what the control system and the IoT application make up is our cybersecurity test bench, which is our overall system. So we wanted it to be safe for our client, ABS. So we put up safety panels around the whole system so that no one can stick their finger or hand in there and get hurt. Nothing's going to come flying out anywhere. And then we also made it able to fit on a desk. So as you'll see in the demo, it's about 3 by 2 feet, 2 feet tall. And we modeled it after a live system.
Cool. So as far as our validation goes, we had 3 main areas. But the first one was getting the feedback for the rudder. And to do that, we utilized the potentiometer, which is a sensor with a knob. And as you turn the knob, it changes the voltage on the output. And what we did is we glued the potentiometer down on the axis of rotation of our rudder. So when the rudder spins, it will spin with the same angular displacement on the potentiometer, and we can get a range of values and convert those into degrees of rotation. And in calculating our conversion ratio for the voltage to degrees of rotation, we had to tune it. And to do this, we took 2 readings, one at the minimum value, which was minus 35 degrees, and then one at positive 35 degrees. And that gave us a range of voltage values, and we could model that and convert that voltage to a degrees of rotation. And for validating our potentiometer to make sure that it was actually giving us correct readings, we looked at the accuracy and precision by graphing several measurements and then lining them up on a protractor to make sure that they were correct, and then analyzing the graph to see the precision. For our propeller, we had our system sensor, which is on the right. That's the one in our system. It's an infrared distance sensor, and it can tell if there's a wing of the propeller in front of it, and it can count the number of times that it spins past it, and we can convert that into an RPM measurement through the software. As far as validating the accuracy, we bought a secondary sensor, which is on the left, which is store-bought, and we can assume that that's the most accurate that we can get, and then we can compare the readings that our system sensor gets to the secondary sensor and make sure that it's working correctly. And lastly, we also have the last portion of our system is in the cloud, and it's on a database. And we wanted to make sure that the API can execute at least under 200 milliseconds, which will at least make it so that when we're using it, it seems fast enough that if something goes wrong, if it's hacked, then we can tell that it's taking longer than normal. So 200 milliseconds will allow it to work smoothly. Next slide.
Going into some of the methodology and designing this system, what me and Daniela had to do on the mechanical side and really the physical side, the hardware side of this project, was design it all on CAD or computer aided drafting. And so we used SolidWorks to do that. We looked for parts that we looked for parts online that we could go and pick up from Home Depot or Lowe's, and we designed those things first. And we kind of configured the system in a forward manner to make sure that as we added parts, the functionality remained. And we also conducted motion studies that would simulate the actual moving parts of our system. And we made sure that as we went along, we were meeting design requirements. So that's kind of how the design went. Once we got to this semester, this fall semester, we began construction of our system. And so at this point, we had already kind of configured a list of the parts that we wanted to buy. And we also had some parts on the system that we had to creatively make so that other components of our system would function properly. And so we sent a bunch of those parts to the 3D printing lab here at the University of Houston. And that actually helped us out a lot with maintaining the budget and keeping costs low. And we also, during the semester, we integrated both the software and hardware of the system. And Sean talked a little bit about the validation of the electrical components in the previous slide, but throughout this semester, Daniela and I were able to really validate all the things we did on the hardware side and the construction of the system by seeing Sean and Josh accurately manipulate the system through the software. So our system integration was a success, and that'll move us directly into our challenges. So during the construction, our first problem was that we ordered a linear actuator that was larger than we expected. And that was kind of we kind of had to throw a lot of the things out of the window and start from kind of scratch and redo things. Another challenge that we had was access to tools. None of us are builders or anything, and none of our families had too many tools. So you can see in the middle picture that we constructed a table saw using a table that we built and a circular saw. So it was nice that worked. Other problems we had were with the linear actuator, we actually lost feedback capability in our linear actuator. And like we talked about the potentiometer earlier, that was kind of our remedy to that problem. So we placed that potentiometer in the middle of the rudder stock cap, and we were able to see the angular displacement based off different voltage readings from the potentiometer. And another challenge that we had that really Josh and Sean had throughout this process was multi-threading on the microprocessor. And those are really our challenges throughout this project.
Cool. So some of the main accomplishments we had over the course of the past year was finally getting the software and the motors to integrate completely. So we started testing the motors with a keyboard, and once we had that functionality, we had to, like I said, we had to do some validation to make sure that it was accurate and precise enough. Due to the nature of this project, that was very important. As far as integrating everything went, since we have two fields, we have mechanical and electrical working on the project. We had to integrate the frame with the motors and then do the testing over again once it was actually on there. Another thing we had on the software was we created a user interface, and we needed to make sure that the user interface could control everything as well. And part of that user interface was updating certain measurements that we could send to the database and then retrieve them. And on the bottom picture, you can see results that we had validating that our API was working. I think those are response times for each of the calls that we use. And we wanted to make sure that those were under 200 milliseconds as part of our validation as well. Next slide. Cool. So now we're going to go over some of the results that we had from our validation plans. For the tachometer, which is to measure the RPMs, this is a graph of our secondary sensor and our system sensor on top of each other so that you can see that they correlate fairly accurately. And this was good news. That means that the way that we did our infrared sensor was working properly, and we went on to do some more tests. But for this one, we vary the speed from 0 to 10, which is the RPM number that you'll see on the user interface. And as we increase the speed, we can see the RPMs rise in a linear fashion, which means that it seems to be working really well. So next slide. So this is another result for the tachometer, and this is looking at error between the two sensors over time. So the red marks on our graph show the thresholds of error that we need to stay within in order for the RPM number to align correctly on when it's being sent back to the user interface for feedback. And it's really just rounding errors. It needs to be within 0.5 degrees plus or minus. And this one stayed well within the margins of error, and it seemed to be both accurate and precise. The mean was around 0.079, and this is when the potentiometer was supposed to be at 0 degrees. So yeah, that looks as 0.079 is very accurate. And the standard deviation of our variation was very low, so we could tell that it's precise as well. Next slide. And lastly, this is our results for our API response times. In the gray line at the top is a really important one, because that one is used over and over again, and that's the one that we needed to be under 200 milliseconds for sure. And it seems to be just under 200 milliseconds, which fit our goals just well. And so, yeah, our API seems to work smoothly, just as we needed it to. Next slide.
So in conclusion, our project works properly. All the system integrations worked well, and we're under budget. It fits where it needs to fit. The user can control the system with the keyboard. The instructions will pop up on the screen to show you what to press to do what. So you can raise the propeller speed or change the direction of the rudder, and the database can store and retrieve information from the system for the cybersecurity engineers to use. And there'll be a virtual little screen on top that you'll see in the demo right now. And that's it.
And yeah, that's the presentation.
And now Josh is going to show you the demo.
Yeah, so can everyone hear me?
Yeah, Josh, I'm passing over control to Harshal, actually.
Yes, to Harshal. Okay. So I think everything's good. Now I'm going to kind of give you an overview of our system, kind of show you everything with the camera, and just talk through exactly all the electrical components that went into it and how it functions. So this is the system as a whole. If you can see it, pretty much what you saw in the first picture. We go here, we can kind of see our linear actuator. And what this does is it essentially acts like a ram would on an actual vessel. So it pushes this cart across the track. And as that cart moves along the track, it's also connected to our rudder down here. And as it moves along this track, it'll cause the rudder to turn. Another key component is the propeller. So this propeller is actually hooked up to a brushed DC motor. And that DC motor gets up to 1,000 RPMs for our system. And that is what causes the propeller to spin, is that brush motor. So if we go a little bit more into the electronics or the 3D printing, if I come here, you can actually see our angle measurement system. So all the parts in gray and black are actually 3D printed, and we needed that 3D printing because we wanted it to fit on our system and work exactly how we designed it to. Inside of here, you can kind of see a potentiometer. And that potentiometer is attached to the rudder so that it turns as the cart is moving. And we get the voltage feedback from the potentiometer that changes as the knob is turned. And we convert that knob, or we convert those voltages into angles so that we know exactly where our rudder is positioned. Another method that you can use to tell the rudder position is the protractor down below. And you can kind of look down there as kind of a rough estimate to see where your rudder is and where it should be. Now, if we take a little bit more into the electronics of the project, let's see. So the little black chip that you're looking at right now, that's actually our motor driver. All the motor driver is for is it pretty much sends control commands or control electrical signals to our different motors, both the linear actuator and the brush motor. Behind that, you can kind of see that large black object. That's our battery. Our battery is about 8 amp hours, and we needed that battery instead of like an electrical outlet because all of our motors require a lot of amps and a lot of voltage, and this battery gives us the perfect amount of that. We come over and look at our control electronics. In red is our MSP microcontroller, and that one's primarily used for data collection and hardware control. So that one really tells the motor, okay, move this much, move that much. The one in green is a Raspberry Pi, and that one's primarily used for database connectivity and for the user interface. So what the user sees and what the user has the ability to see is our screen. And you can't see it right now primarily due to the lighting. But on the screen, we have an image of the rudder that they're going to be able to control. And they're able to see hardware data here. And then below that, they're able to see the simulator data. So that's actually what they told it to do. And the hardware data is what are the sensors reading. And if you see any discrepancy between what you told it to do and what are the sensors reading, then you know that there's some malware or there was some type of vulnerability introduced to your system. You can also see on the screen the database data located here. And that is the data that's currently stored in your database. So you'll have like an overall view and capability to send and retrieve data from a database that's running in the cloud. So I'm gonna reposition the camera real quick, and I'm going to have all the parts moving and we'll get a good visual of everything. So first I'll show you the brush motor and the propeller, which you can see on the left of the screen. So all you have to do to move this is press up on your keyboard and that'll change the speed. You can also press down to decrease the speed. So I'll do that now. So if I press up, we're at our first speed. So this is like the lowest speed. If I keep going up, you'll notice it gets progressively faster. And the user is able to control all this through the keyboard. So I'll turn it back down, bring it to a stop. Now I'll take it to the rudder so we can see the movement on there. Okay. I'm just going to position the camera here. I can turn the rudder by just simply pressing the left or right keys on my keyboard as well. And you're not able to see, we're not able to get a good visual on the screen, but on that little tablet that I showed you that's located on the top, the user is able to select, what distance or length they want to go at. And it directly correlates to the protractor that you see below. So able to move the rudder in different positions, and we can increase the propeller at the same time. If you can see the propeller moving in the back. That pretty much covers the movement of our project. A few more things that I should touch on, but you're not able to quite see. There is a lot of data collection capabilities with our project. So if the user wants to see, what is the potentiometer actually reading at this position, at -35 or 35 degrees, they have the capability to press, I think, Q on the keyboard, and it'll go through a series of tests and data collection. And then once it's done, it'll export to a CSV all the different values that were read at that certain position. So you can use that for any type of data collection or data analysis that you may want to perform. Also, as far as the database, I know I kind of touched on it, but we currently have a database server running. Right now, it's MongoDB is what we're using for it. And the user, if they press S on the keyboard, it'll send data to that database, primarily through the internet. And then if you press R on your keyboard, it will retrieve whatever is currently in the database, and it'll display it on the blue screen that we saw before. And that's an overview of our project. And that kind of touched over the different aspects of it. Are there any, I guess now we can open it up to different questions. Yeah, so does anyone have any questions or comments? No need to be shy. Feel free to throw anything at us.
Hey, this is John Jorgensen from ABS. I'm really impressed by the project. It looks really impressive, and I think it's really cool how you put it together. Tell me what the most challenging aspect of this was for the team in general. Now, each of you has individual skills and insights based on where you've come from and where you're going, based on majors, interests, and things like that. But there were probably inevitably at least one, possibly as many as 3 areas in this particular project that you would have all looked at one another and said, who knows how to do that? What were those areas and what did you learn?
I'll give a quick area real quick from my perspective. I'm not really fully aware with software manipulation and running all these systems at the same time. And throughout the conception of this project, I learned so much more about specifically multi-threading and being able to manipulate several components of a system several components of a control system at once. And working with Josh and Sean, I learned a lot about that. And I learned a lot about, the necessary coding that goes in behind that and just things of that nature.
Yeah.
Okay, what did you learn about testing your software there? And Josh, feel free to jump in on that.
Yeah, I can go ahead and jump in. So a major thing that we learned when it comes to testing our software is to use software to write your tests. That was a big thing. So I think a little bit early on in our project, the primary way that we were using to test the software was really just run it and then see if it works and then kind of record that. But what we more moved into was we need to actually write software tests and then have the software collect any data to show, okay, does it work? And then the benefit of that is that when you write the test using software, you can run those tests over and over and over again. So I guess a good specific example of where we implemented this was with the database communication. So all that software is like running in a separate server. So we use like a testing framework, a JavaScript testing framework called Chai and Mocha. And using those frameworks, we were able to get a lot more information than if we would have just, done it a few times and then said it worked. We're actually able to write tests in a way that it tested fully the functionality of our project. And it actually gave us timestamps on how long does this function take to execute. And we were able to put it through multiple different scenarios to identify any key failures.
You've come across and elucidated a key factor in systems engineering. It's understanding what you are looking for as part of test so that you can load the deck, so that you can limit behaviors to what it is that you're testing and look for any anomalies that come up as a part of that. So the fact that you used the testing frameworks is a big plus, and that's a big learning point. These things all contribute to the systems engineering education that you will all go through as you graduate and move into systems in the corporate world. As you start working systems and doing actual systems engineering out there, You're going to learn some things like this. And every now and then, you need to be able to get together and chat about the things that you're learning, because it helps to cement the lessons in place. It's very important to bring these lessons together so that you realize that, hey, these are the things that I've learned. So that's excellent.
Yeah, thank you.
I might have a non-engineering question because I'm not an engineer, which is what do you all want to do next? What do you see for your careers next? Recognizing that this is an unprecedented year.
Yeah. So I guess I'll start off, like, for sure in the future, I want to pursue like software engineering, any type of like software engineering role. So, you know, we had a lot of programming for this to work on both the database communication, all the embedded systems, the controllers, microcontrollers, and that really excited me. So I really love the software engineering aspect, and I see that in my future career.
Yeah, and yeah, and I'm really interested in robotics and machine learning and automatic controls, and real-time operating systems like multi-threading, things like that, and yeah, just embedded systems in general. And I don't know, there's a lot of applications of IoT, and you can almost apply like an embedded system like field to like any sort of other field as well. So I don't know, there's a lot of things to go forward, but yeah, at this point, just learning more and more and more and seeing how I can apply that and create projects. Because whenever you have a project, it kind of like shows, it's like a benchmark to show like what you can do now. So yeah.
Jumping off what Sean said, I'm not entirely sure. There's so many things to learn about, and you know, my focus will shift as I grow and learn and become who I'm becoming. But currently, I'm going into solutions engineering. In the future, I want to learn more about product management, project management, possibly get into some research and development on the more technical end. But for now, I'm just like doing as much as I can to learn about things and keep discovering my niche.
Yeah, just going off of what everyone else said, I'm really open to any opportunity. That's why I went into mechanical, because of the endless opportunities. You can go for anything. So I'm just really wanting to get out into the world and meet different places and learn different people and learn what they've learned and incorporate what I've learned. And so then everyone can learn. But yeah.
That's awesome.
Hello, I have a couple of questions. So I think the project looks fantastic. I'm really proud to have it in our lab. I think it's great that you guys came together. The fact that it's all running off of one Raspberry Pi is just amazing. It's all completely integrated. That's pretty neat. I do have a question though. Have you actually thought of any cyber scenarios to use with the project?
So I think connecting it to a database, and so having it as an IoT device was one thing that we considered. And I mean, like with the growth of like IoT devices, like everything is more vulnerable. So at least having a vulnerability that didn't necessarily need to be there, but we added it anyways, is one thing that we considered. A lot of the things that we wanted to do, we wanted to show what the rudder and the propeller should be, and then above that show what it actually is, and kind of contrast like the actual from the desired. And so if something does go wrong, it becomes a lot more evident. But I don't know if
Yeah, I mean, just to add on to that, the focus of our project wasn't really like figuring out different ways to hack it, but we built it in during the design phase. We focused on designing the system to leave those vulnerabilities to be possible. So like a good example of that is what Sean touched on before, having a database. Initially, that wasn't in the scope of like the embedded systems part of our project, but we decided to integrate that because we know that database security is very important when it comes to cybersecurity. Another example of us like taking the cybersecurity approach into account is having the user have the ability to view all data from our system. And that really is useful because in order to detect if something's been hacked, you need to see and you need to be able to prove that empirically, like through numbers. Having those different things in mind during the design phases really helped us, and having Keon there and Harshal, communicating what they actually do and stuff like that. That really helped us in the early design phases and building a project that could be used for cybersecurity.
Okay, well, that's great to hear. So basically the database and the API are completely vulnerable and we need to figure out ways to hack into them. Okay. That was great.
All right, I have a question for you guys. I know I've been kind of quiet during this presentation. I think it was great. Good job, guys. Everyone did an awesome job. I love the hard work you guys put into it. I love the personalization that you put on your project. It was great. I have two questions. One, where do you see this, if another group of students came in, what aspects of your project do you see that they can grow and expand on as you leave it? What do you see as the next step in it?
Yeah, so like a big next step would be focusing a lot more on the cybersecurity part. So kind of like how I touched on before, we designed the system like keeping cybersecurity in mind, because we wanted to leave some of those vulnerabilities open so that they could be, developed further in the future. And when we pass it on, cybersecurity engineers can actually work on it. So like as a future extension of this project would most definitely be, going into the code, seeing it changing something, seeing how that affects things, doing like a full cybersecurity breakdown on the different vulnerabilities that are possible, either with the database or maybe in the embedded system as a whole. That would most definitely be like a further extension that could be done on this project.
All right. And my second question is, can you, from the electrical standpoint and from the mechanical standpoint, can you guys elaborate on what the working with ABS and getting introduced to some of the people around ABS has meant for you guys?
Yeah, I'll jump on that real quick. Working with ABS, specifically on this project, taught me a lot about the maritime industry and how things work in it and the standards that you guys look for. And in implementing those standards on a tabletop, bench, we've learned a lot. We've learned how to scale down from the research that we conducted on our own, and just framing things in our mind and putting it physically, and then the system integration to manipulate these physical systems. It's all been a learning process, and the learning process has
on the other meeting. So I cannot hear both. Yeah, it's all going on. Switch to audio.
I don't think you're muted, Angeliki.
Yeah, Angeliki, we can hear you.
Well, anyways, just to wrap that up, the learning process has been the learning process. If Josh and Sean want to jump in on that.
Yeah, and I think like Keon and Harshal were really helpful in like making sure that we were like on track and things like that, and just working in a multidisciplinary environment. Now that we had electrical and mechanical, and we're working with like Keon and Harshal, who are in cybersecurity, and that's a new experience altogether. So they kind of helped work us through that. So yeah.
Also, I want to mention Brendan for kind of pushing us in the direction of the overall design. Josh mentioned the RAM system. that these rudders actually work on. And Brendan definitely showed us that, I want to say in February. And Danielle and I kind of took that design and ran with it and kind of created our own RAM system to give to you guys.
Well, thank you. I can't say thank you enough. You guys did a great job.
Thank you.
So much for giving our team this opportunity.
Yeah, thank you a lot.
Thanks for presenting this, guys, and good luck with everything. Clearly a smart crew. No pun intended on that one.
Thank you.
Yeah, it looks
That's
great.
Thank you.
And somebody has some pretty good 3D printing skills. I noticed the ABS logo on the rudder.
Yeah.
Opportunity.
Great. Well, before, if there's no more questions, before we log off, I wanted to take a group picture. So if you can turn your camera on just for a few seconds, that would be great. And just so we can see everyone who attended. Great. All right. 3 seconds. All right, I got it. Perfect. So once again, thank you so much. Thanks everyone. You guys did a fantastic job. Thank you everyone who attended. We'll be doing a follow-up story on this Capstone project that will be live on the website in early 2021. So that will be available and you can send that out too. So like the email says, really great to just support our future engineers, our future cyber engineers. So yeah, we'll, and also make sure you're following us on social media. Quick plug, because we're also going to do, I'm also going to do a recap on there about our time today. So really appreciate everybody tuning in.
Thanks, guys.
Thank you.
Thank you.
Bye.